Greetings and welcome to lecture number 17 on fluid dynamics, the topic laminar flow. This lecture we are going to discuss the numericals on all three cases, that is laminar flow through a circular pipe, laminar flow between fixed parallel plates, and coated flow. In order to solve the numericals, we have to memorize these expressions logically. So these are the parameters we have to memorize for solving various numericals. And these are the three cases, that is pipe flow, Poiseuille flow, that is called as flow between fixed parallel plate, and the coated flow. So as far as local shear stress is concerned, in all cases, local shear stress is directly proportional to either radius or distance y, that is perpendicular to the direction of flow, and the same here. So pressure gradient, so linear variation of local shear stress, so minus dabba p by dabba x is common. So the second term is r by 2 here. The second term here is b by 2 minus y. And here only one term is added. So the same term with mu into u by b. That is in shear stress expression, we have to add Newton's law of viscosity plus expression of tau in case of a Poiseuille flow. So this way you can memorize. Maximum, no need to memorize this expression because if we know where we get maximum shear stress, generally at the boundaries. So here in small r can be replaced by capital R. Here we have two values of tau at both boundaries. At lower boundary, it is a positive value, and upper boundary, it is a negative value. So it's only b by 2. So these are the maximum shear stress. No need to memorize this. If we memorize the local shear stress expression, we can derive from this. Similarly, local velocity we have to memorize. So in this case, local velocity, it's 1/4 mu minus dabba p by dabba x, r square minus capital R square minus small r square. The same equation is there, only instead of 4, 2 is there. And instead of this, that is dy minus small y square. So quite similar equations, only you have to memorize the differences in the equations. And in this equation, again, one more term is added there, that is u by b into y. So that term is only added in local velocity. Maximum velocity, again, if we know where maximum velocity arises, that is at the center. So here only by put r is equal to 0, we get this value. Here y is equal to b by 2, we get b square. So if we know the condition where we get the maximum velocity, we can develop the expression of maximum velocity from that. Mean velocity, if we know that this way we can memorize the expression of mean velocity in terms of maximum velocity. Because maximum velocity we can develop from local velocity. And mean velocity expression is comparatively easy to memorize. That is, in case of pipe flow, it is 1/2 Vmax. In case of Poiseuille flow, it is 2/3 Vmax. So some expressions are not applicable for coated flow because there are various possibilities in coated flow. All three pressure gradients exist, that is positive, negative, and zero pressure gradient. So for sake of convenience, we are not going to use the expressions of other parameter, that is maximum flow, maximum velocity, mean velocity. Discharge expression, we don't need to memorize the discharge expression. So this expression only if we know the mean velocity. So from mean velocity, we can calculate the discharge velocity. So even this is slightly complicated expression. So that's why no need to memorize the expression of discharge. Pressure drop expression, yes, we have to memorize this expression. That is P1 minus P2, 32 mu L by D square, that is for pipe flow. And only 32 is replaced by 12 and D is replaced by B. That is 12 mu VL by B square. So these two expressions we have to memorize. Only one expression and the changes in other expression. So actually we have to memorize only 3 expressions and 4 expressions. And based on 4 expressions, we can develop other expressions. So for example, local shear stress, local velocity, then mean velocity in terms of maximum velocity, and the pressure drop equations. So remember, while solving problem, we have to utilize only these 4 expressions. And I'm sure there are different ways we can calculate the answer or we can obtain the answer. But if we stick with these four equations, because there are many equations in fluid mechanics, but if we stick with these four equations, then you won't find difficult to solve any kind of numericals. So any kind of numericals we can solve. So again, I repeat, so only we have to memorize four expressions: expression of local shear stress, expression of local velocity, mean velocity in terms of Vmax, that is maximum velocity, and last one is the pressure. So these expressions we have to memorize. Now we'll see the numerical in each case. So first we consider the pipe case. An oil of viscosity 9 poise with a specific gravity 0.9 is flowing through a horizontal pipe of 60 mm diameter. If the pressure drop in 100-meter length of the pipe is 1800 kilonewton per meter square, determine this parameter, that is rate of flow, central velocity, that is obviously the maximum velocity, total frictional drag. Total frictional drag, that is the force it is asked. So first of all, we have to calculate shear stress, and shear stress into area, that is circumferential area, gives us the total frictional drag. Then power required to maintain the flow, that is the power force into velocity, that is frictional drag into velocity. That way we can calculate the power. Or we can, other way, that is also the delta P known to us. So delta P into Q, that expression also we can use. Then the velocity gradient at the pipe wall, that is dabba y by dabba, so dabba v by dabba y at y is equal to 0. So that we can obtain by using the expression, that is tau expression also we can use there, and using Newton's law of viscosity also we can obtain. And finally, the velocity and shear stress, that is local velocity and local shear stress. So we restrict our use with only these four expressions. Now we can obtain that, we will see. So first of all, we'll write the given quantities. So these are the given quantities. So viscosity is given, we convert into appropriate unit. Specific gravity is given. Diameter of the pipe is given, so we can calculate the area. Pressure drop in 100-meter length of the pipe. So delta P, that is P1 minus P2, that is 1800 kilonewton per meter square. So this is delta P value is given. Now these are the given quantities. Now we have to first calculate the rate of flow. So this P1 minus P2, and if the length per unit length. So if pressure drops in 100-meter length, so indirectly dabba length is also given. So indirectly P1 minus P2 by L, that is dabba P by dabba X is given. Now we start with, that is rate of flow. Rate of flow we can calculate with the help of mean velocity. Now here from the given information, mean velocity we can calculate by using the expression of pressure drop. Because mean velocity, in which equations mean velocities are in which equation mean velocity is involved, that is in two expressions. V mean, that is equal to 1/2 Vmax, and P1 minus P2 in this case is 32 mu L by d square in that V mean. So either of two equations we can use, but at present from the given information, this equation we can use, that is a pressure drop equation. So we have P1 minus P2 that is equal to 32 mu VL by d square. Now in this case, P1 minus P2 by L is given, mu is given, the diameter is given, we can calculate velocity. So by putting all these values, so P1 minus P2 by L, that is nothing but 18 kilonewton. So 18,000, we can say 18,000, that is P1 minus P2 by, because we convert into Newton per meter square. Then mu already known to us, length, that is or we can consider this P1 minus P2, length is 100 meter, then diameter is 0.06, we can obtain the velocity 2.25 meter per second. The first answer. In central line velocity, if we know the mean velocity, then the relation between mean velocity and after that we have to calculate the rate of flow. So Q is equal to area into velocity. So from that we can calculate rate of flow. Secondly, central line velocity is the maximum velocity. Now again we have to use the equation, that is mean velocity known to us. So we can calculate from that expression that is the maximum velocity. So V is equal to 1/2 Vmax. So from that we get the expression equation. That is Vmax is equal to 4.5 meter per second. And the total frictional drag over 100-meter length, so that is FDR, FDR. So that is obtained from shear stress. So maximum shear stress, even if we know the local shear stress, we can put the value of small r is equal to capital R. We can calculate the maximum shear stress. Because at the wall, generally the frictional drag is obtained. So at the wall, we have to calculate the shear stress at the wall. So that is tau max. So tau max into area. Area is pi dl, that is circumferential area. For shear force, we have to consider circumferential area, that is pi dl. For pressure force, we have to consider flow area. So where to take which area, that we must understand, because shearing action takes place on the circumference. So pi dl is taken, that is F is equal to tau max into pi dl. Now everything known to us, by putting all these values, we can calculate the total drag force. Then the fourth one, that is power required to maintain. So power required, that is force into velocity, that one expression, or we can use this expression dp into q also. That expression also we can use. Both quantities are available, so we can use this expression, that is force into velocity. So by putting the values, we can calculate power, that is 11.45 kilowatt. Then velocity gradient at the pi 4, that is obtained from maximum shear stress. We apply the Newton's law of viscosity, that is tau is equal to mu into dabba v by dabba r, and that is at r is equal to capital R, that is at the wall it is r. So this we have to calculate. So tau max known to us, mu known to us, we can calculate dabba v by dabba r at r is equal to 0. And finally, the local shear stress and the local velocity. Local shear stress is expression of local shear stress is this. Putting all the required, because R the velocity and shear stress at 8 mm from the wall. So this is not actually R. R is nothing but that is capital R, that is 0.03 minus 8 mm, because it is 8 mm from the wall. So R is measured from the center. So here sometimes student make mistakes that taking the value of R, that is directly, this is not R. This is the distance from the wall. So R is considered, that is 0.03 minus 8 into 10 is to minus 3, that is R. So by putting that value, we get tau. Similarly, we can use the expression of shears local velocity. So these expressions, again, everything known to us. So we can calculate the local velocity. So that's it. So we have used only the expression of local shear stress, local velocity, pressure drop equation, and relation between V. So 4 equations only we have used. And these equations we can derive. If we know this equation, this equation we can derive it. So that's it. This is the numerical on pipe flow. Now one numerical will take on 6 parallel plates. So that is 2 parallel plates kept 100 mm apart, have a laminar flow of oil between them. So the length is given, that is, sorry, not length, it is capital B, that is 2 plates are placed at a distance 100 mm apart. With maximum velocity is given 1.5 meter per second. Calculate the discharge per meter width, then shear stress at plates, the difference in pressure between 2 points. Now this is L, that is 20 meter apart. The velocity gradient at the plates, then the velocity, that is the local velocity, 20 mm from the plate. Maximum viscosity. So given quantities, V is given, Vmax is given, mu the dynamic viscosity is, and the length is also given, that is 20 meter. These quantities are given. Again, we have to use judiciously select the expressions. Now, in order to calculate discharge, again, we have to rely on 2 expressions, either expression of pressure drop or expression of Vmax, if Vmax is given. Because in these 2 equations, V involves, that is mean velocity. If we get mean velocity, we can calculate discharge. So here maximum velocity is given. So from maximum velocity, that is in this is the case where the relation is V mean, that is equal to 2/3 V max. So from that we can calculate V mean, and then we can calculate discharge. Let's see. Discharge, that is V is equal to 2/3 V max. So from that we can calculate V, that is 2/3 of 1.5, that is 1 meter per second. Then we can calculate discharge. So discharge in this case is per meter width, that is V into B into W. That is width. So width is considered as unit. So the discharge comes, that is 0.1 meter per second per meter. Then the shear stress at the plates, that is tau max. So if we know the expression of local velocity, then we can convert that local velocity into maximum velocity, that is plus minus. So this is the expression of tau max. Plus minus delta p by delta x, b by 2. So b known to us. Delta p by delta x is still not given. So now we have to calculate this delta p by delta x first, and then we can calculate this local shear stress. So delta p by delta x is involved in V max equation. We know the V max, already know. If, from local velocity, we can derive the expression of V max. So V max is equal to B square upon 8 minus delta p by delta x. So from that, we can calculate minus delta p by delta x. Then we put this delta p by delta x here to calculate maximum shear stress plus minus. So check any other option is there for calculating this pressure drop. This is pressure difference. Yes, there is another option, that is we can calculate this pressure difference or delta minus delta p by delta x using the pressure drop relation. So pressure drop relation, that is P1 minus P2, that is equal to 12 mu VL by P square. So from that equation also we can calculate delta P by delta x. So by taking P1 minus P2 by L on one side, that is equivalent to minus delta P. So 12 mu is given. Then L is 20 meter is given, then divided by B square. So only quantities. So from that expression also we can calculate this. So even because this is derived from local velocity. So local velocity expression we have to memorize. So from that we can derive this. These are the alternative ways I am telling. So anyway, that depends on the individual how you apply your equations, how you apply your knowledge to solve the numerical. Then the pressure difference between 2 points, 20 meter apart. So minus delta p by delta x, that is equal to P1 minus P2 by L. So once we know this, that we can easily calculate this pressure difference. The pressure difference is us, not this is a pressure gradient. So minus P2 into L, that gives us the pressure difference. Then velocity gradient at the plates. So that is again obtained from tau max, because tau max already we have obtained. So velocity gradient at mu is equal to delta v by delta y at y is equal to 0 at y, or y is equal to b. And the same. So everywhere velocity gradient is same. So that is delta v by delta, sorry, this is the printing mistake. That is delta v by delta y at y is equal to 0 or y is equal to b. That is 60 s raised to minus 1. So this is velocity gradient at the plates. Then velocity at 20 mm. So that is a local velocity. So we have to use the local velocity expression here. So 1 upon twice mu minus delta p by delta x dy minus y square. So putting the value of y is equal to 20 from the lower plate and minus delta p by delta x, that is already known to us. So we can all quantities on the right hand side known to us. We can calculate local velocity. So this is the way we can solve the problems. So only by memorizing these 4 expressions, we can solve n number of numericals. Even for more numericals, you can refer any book. Only based on these 4 equations, try to solve the example. Use your, and that way you can develop your analytical ability. So how to use the equations and how to use the equation so that minimum time is required or minimum labor of uh, calculation is required. So as far as possible, the equations you're supposed to use, which are based on the given quantities rather than obtained quantities. Means in that in some cases, the obtained quantities, if they are wrong, then your second answer also become wrong. So you, as far as possible. So that again depends on the individual. You apply your knowledge to solve the problem. So this is the example on a Poiseuille flow, that is flow between fixed parallel plates. Second, that is in Coite flow, a liquid of viscosity 0.9 points is filled between two horizontal plates 10 mm apart. The upper plate is moving at a velocity 1 meter per second with respect to the lower plate, which is stationary, and the pressure difference between two sections 60 meter apart is 60 kilonewton per meter square. Determine the velocity distribution, discharge, and shear stress on the upper plate. So this problem is based on the Coite flow. So Coite flow, we are memorizing only two expressions, that local velocity and local shear stress. And so from based on these two only, we have to obtain the expression. Obtain or solve, we can solve the numericals. So from given quantities, dynamic viscosity is given in poise. We have to convert it into Newton second per meter square. Is filled between two horizontal plates 10 mm apart. So B value is given 10 mm. We convert it into meter. Upper plate is moving with 1 meter per second. So we are using notation for plate velocity, that is capital U with respect to lower plate. Lower and the pressure difference between the two sections. So the length is given. Two sections are 60 meter apart. So length is given. This pressure difference is P1 minus 2, 60 kilonewton per meter. Velocity distribution is asked, means the velocity distribution equation we have to develop in terms of y. So we know this is the condition, stationary plate, wing plate. So as far as possible, every numerical, if you draw the diagram, it is always good, because diagram is nothing but your graphical representation of the statement. So if your diagram is correct, the examiner can understand that he understood the statement as well. And it will be convenient for solving numericals. Maybe in previous two numericals, we do not require that because these are the simple diagrams. Even if you memorize, but as far as possible, wherever you can, you draw the diagram. Velocity distribution expression, that is only addition of this term, the expression of fixed parallel plate. Now, in this case, only y is unknown. We have to develop expression of velocity. So v expression, so dabba p by dabba x is given, u value is given, p value is given, u value is given. So by putting all these values, we get the expression of v in terms of. Now, discharge per unit width. So for that, we can integrate this expression with respect to y, and the limits of integration is 0 to b. So discharge, that is 0 to b, v dy, and after integration, we can calculate the discharge, that is 0.925. And the shear stress on upper plate. So shear stress equation we can use, that is upper plate, that is at y is equal to b, so mu into dabba b by dabba y at y is equal to b. So here we can use the expression of shear stress also, and putting the value of y is equal to b. That way also we can solve. Or by using first principle, that is the shear stress at the plate, that is everywhere in laminar flow, that is in terms of local velocity, that is mu into dabba b by dabba y at y is equal to b. So we're putting the expression of y v in terms of y and differentiating this, and we get this expression. That is, if we differentiate this, it is 155 minus triple 4 times 5, 55 is into 2y. So put y is equal to b. So put y is equal to 0.01, and solving we get this expression. So this way you can try many problems and try to solve using only 4 expressions, limited to 4 expressions, so that no need to memorize the other expressions. So I once again repeat, you have to memorize only expression of local velocity, local shear stress, then the relation between mean velocity and maximum velocity, and pressure drop equation. That's it. These 4 equations, and these are comparatively easy to memorize. So maximum velocity can be obtained by putting the condition, and the discharge can be obtained by using the mean velocity. So you need to use the expression of discharge for calculating discharge. So most of the books, such the problems are solved by directly using the expressions. That is good that if we know the if we have the expression with. But exam point of view, with the help of minimum equations, how we can solve the numericals. So that is the crux of solving problem in laminar flow. Only you have to use that table what I have initially shown. So that table you have to memorize in 4 expression in that table. So before going for examination, so if you memorize once again, revise that, you will not find the to solve the problem on the laminar flow difficult. Any kind of problems. There is a repetition only. The questions will be the reshuffles. That's it. Yes. So not much varieties are there. Uh, so that's it from this particular lecture. At the end of this particular lecture, you will be able to calculate flow parameters in following cases. That is laminar flow in circular pipe, laminar flow between fixed parallel plates, and laminar flow in coite flow. That is plate parallel plates where the lower plate is fixed when upper plate is moving with some velocity. So that's it from this lecture.